Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book Retrolinear. The subject of this lecture is the characteristic polynomial of a linear operator, of a linear transformation. We'll get started by reminding you of what eigenvalues and eigenvectors of matrices are. Let A be some n by n matrix, a square matrix. Then a scalar lambda is called an eigenvalue of A if you can find a non-zero vector x, column vector x, such that when you multiply A by x, when you find A times x, you get lambda times x. So A times x is a multiple of x, and it's lambda times x. That vector x is called an eigenvector of A corresponding to lambda, and there will be quite a few eigenvectors corresponding to a single eigenvalue. In previous videos, we have give you motivations about why this definition is useful, why defining eigenvalues and eigenvectors might be useful, and we have also talked about how you might go about finding them. In fact, in the process of finding them, we defined something called the characteristic polynomial, which is the subject of this lecture. So let me remind you of that. So again, how do we find eigenvalues and eigenvectors? Well, what we noticed was that if you have a square matrix A, an n by n square matrix A, then lambda is an eigenvalue of A if and only if the determinant of lambda I minus A is 0. In is the identity matrix, n by n identity matrix. When you multiply lambda scalar by the identity matrix, you just get the matrix that has lambdas down the diagonal. Then you subtract A, again, you get an n by n square matrix, and then you take the determinant of that. And those lambdas that make that determinant equal to 0 are the eigenvalues of A, and those are the only eigenvalues of A. And also, eigenvalues of A corresponding to lambda are going to be precisely the non-zero elements of the null space or the kernel of lambda I minus A. Okay, so this is again was the subject of a previous video. Because of that, we made the following definitions. That determinant of lambda I minus A, we called the characteristic polynomial of A, and the null space, the kernel, null space and kernel are different words for the same thing. The null space of this matrix lambda I minus A is called the eigenspace of A associated with lambda. And what we want to do is we want to talk about the characteristic polynomial a little bit more. The characteristic polynomial is important because its roots, the values of lambda that make it equal to 0, those are the roots of that polynomial, are exactly the eigenvalues of the matrix. So let me just repeat myself. A and n by n matrix, then the determinant of lambda I minus A is again an n by n matrix, and so you can find its determinant. But as long as lambda is an unknown, this will be a polynomial, and it's called the characteristic polynomial of A. And what we write it as is Char A. So when you see this notation Char A, that means find characteristic polynomial of A. Now, something to note that if you have an n by n matrix, then this is a polynomial of degree n in lambda. And the roots of this polynomial are the eigenvalues of A. So why is it a polynomial? Because what is lambda I minus A? A is a bunch of numbers. Lambda is an unknown. When you multiply it by identity, you get lambdas down the diagonal, and then you subtract. And so you get an n by n matrix that in every row and every column, in fact, in every diagonal entry, there's something with lambdas. There's maybe a lambda minus 2 or lambda plus 3 or such things, but there's lambdas in every one of those diagonal entries. When you find the determinant of that matrix, you're finding elementary products, which means that you're finding the terms of that determinant. All are terms that are products of things that entries, one from each row and each column. So each one of those products will have several number of lambdas in it, possibly, and the most that it will have will be when you find the product of all the diagonals, and that will give you a lambda to the n term. And there won't be any other term that will be able to cancel that out. So you will get a polynomial of degree n in lambda. You're not going to get anything else. You're not going to get tangent of lambda or 1 over lambda anywhere. But with finding elementary products, you're just multiplying things over. And so you will get constants, and constants times lambda. And lambda squared and lambda cubed and all the way to lambda to the n. And so you will get a polynomial of degree n. And again, the roots, the numbers that make the values of lambda that make that determinant equal to 0 are the eigenvalues of A. So let's look at this, an example. Here's a 3 by 3 matrix. Its first column is 1, -4, -7. The second column is 2, 3, 4. And the last one is -3, -1, 5. Then lambda I minus A, I this time is I3, the 3 by 3 identity is going to be this matrix. Lambda -1, 4 and 7 is the first column, and so forth. So again, and then when we find the determinant of this polynomial, this matrix, you can use cofactor expansion, or you can use you can do elementary row operations and keep track of what happens to the determinant as you go along. You will get, and I'm not going to do that in public. There's some things you have to do in the privacy of your home. You get this polynomial as long as I've not made an arithmetic mistake, which I may have. So you get lambda cubed minus 9 lambda squared plus 14 lambda minus 58. So this polynomial is a polynomial in lambda, is called the characteristic polynomial of this matrix A. Now, finding the zeros of polynomials, if it's degree 2, if it's a 2 by 2 matrix, well, it's easy. This is the quadratic. You can use the quadratic formula. The higher degrees is harder. For degree 3, you can actually find there's a 4 and degree 4. There are ways of finding them, formulas, although somewhat complicated ones, usually covered in courses in abstract algebra, where you can solve them. But if when you get higher degrees, then that's not always possible. In fact, there are theorems that say that sometimes you can prove that it's impossible to find a reasonable solution for them. But whatever they are, you can always approximate the solutions, for example, using Newton's methods from calculus, the solutions meaning the roots of this polynomial. In this case, for example, if you put this polynomial equal to 0, you will get that lambda is approximately 8.16 and 40.42 plus or minus 2.6i. The roots are actually two complex numbers and one real number. So if you want to limit yourself to real numbers, then this has only one eigenvalue, 8.16 approximately. But if you expand your set of scalars to the field of complex numbers, then you have 3 eigenvalues. In fact, sometimes when you want to work with real matrices, it makes sense to expand your field of scalars to complexes in order to capture all the eigenvalues and all the eigenvectors of a matrix. And that's something that one often does. And so for that reason, you're not going to see me often say the scalar has to be a real number. The scalar, we can do all of these things in any field, but you might actually just be interested in the real numbers, but it might actually pay to think about a bigger field so that you're not losing any of the eigenvalues. Okay, now what we want to ask in this lecture is that what about linear operators? We had made the case in previous videos that linear operators, linear transformations from a vector space to itself, are another name for square matrices. Square matrices and linear operators are you can go from one to the other. Any statement about one of them should be able to be translated to the other one. So the question would be, can we talk about the characteristic of a linear operator? Can we assign a polynomial to a linear operator whose roots are the eigenvalues of that linear operator? Now the issue is let me remind you that we have defined eigenvectors and eigenvalues for linear operators just like we did for matrices. So if V is a vector space, and if you have a linear transformation from V to V, those things we call linear operators, then any vector in the vector space that's non-zero, and when you apply T to it, you get lambda times V for some scalar, you get a multiple of itself, is called an eigenvector, and that scalar is called an eigenvalue of T. So the eigenvectors for matrices were column vectors, and the eigenvalues were scalars. For a linear operator, the eigenvectors don't have to be column vectors. They're elements of the vector space V, whatever the elements of a vector space V are. In both cases, they have to be non-zero, and the scalars are scalars, and the eigenvalues are scalars, and we have to have here T of V is lambda V in the case of matrices, we have to have AV equals lambda V. So linear operators do have eigenvalues and eigenvectors just like matrices do. So the question is that can we define characteristic polynomial for them? And you might say, well, we can start with T and have a matrix do the job of the linear transformation. So why can't you use that matrix? But there's one little technical issue. That's the fact that T doesn't have just one matrix associated with it. The matrix you get depends on the basis that you choose for V. You have to fix a basis for the vector space to be able to translate the linear transformation to a matrix, to be able to get a matrix for the linear transformation. Again, we have talked in a previous video about linear matrices of linear transformations. If you don't know what I'm talking about, go back to those. So the problem is, well, what if I use one basis and have one matrix for my linear transformation, and you use a different basis and a different matrix, and we might be, each of us might get different characteristic polynomials. Now, if you follow through with all the things we have said about similar matrices and so on before, you will know that already we know, because the eigenvalues of the the operator correspond to the eigenvalues of the matrix, that those polynomials that you found, that I found, will have to have the same roots, but the same roots, because the roots are the eigenvalues. On the other hand, I might say that, well, maybe you get a slightly different polynomial that I do, and I get a slightly different one that I do. And so which one are we going to call the characteristic polynomial? Actually, that's already a proof that won't happen. In any case, the different matrices that we get for T are similar. And to be able to define a characteristic polynomial of a linear operator, I have to make a case that similar matrices give you the same characteristic polynomial. If I can do that, then this project will work. You start with a linear transformation, you find a matrix for it, and then find the characteristic polynomial of that matrix. And if you're right that similar matrices have the same characteristic polynomial, then it won't matter if you use this basis or that basis for finding a matrix for your linear transformation. And again, I gave sort of a proof just a second ago, but I'll now give a formal proof to that fact. So let's say that A and B are similar n by n matrices. What does that mean? The definition of that was that A and B are similar if B is P inverse AP for some matrix P. But the way we understand that, again, look at the video for similar matrices, is that A and B are the matrices of the same linear transformation, but they are matrices with different bases. And in fact, P, that made the invertible matrix P, is the change of basis matrix from one of those bases to another. So this is what I want to prove, that similar matrices have the same characteristic polynomial. So A and B similar, what does that mean? Again, by definition, I'm just repeating myself. There's some invertible matrix P such that B is P inverse AP. That's what it means to say matrices are similar. But that also is the same as saying that A and B are two matrices of the same linear transformation. In fact, that's what's relevant for us. And now I want to find the characteristic of polynomial of B. Well, the characteristic polynomial of B, by definition, is the determinant of lambda I minus B. That's what the definition of this B is, a matrix, and its characteristic polynomial is that determinant. And B is P inverse AP. So I'm finding the determinant of lambda I minus P inverse AP. Both of these are n by n matrices. I can subtract them and find their determinant. Now, what I will say is that you can write this lambda I minus P inverse AP in this other way. P inverse times lambda I minus A times P. P inverse times lambda I minus A times P. Why can I do that? Well, because if you use the distributive law and multiply, the first term becomes P inverse lambda IP, and lambda is a scalar. That can go outside. Identity doesn't do anything, and P inverse times P is identity. So you get lambda times identity again. And the second multiplication, minus P inverse AP, is minus P inverse AP. So this works. But now we use one of the properties of determinants that we know. And what we know is that the determinant of the product is the product of the determinants. So if you have determinant of A times B times C, is determinant of A times determinant of B times determinant of C. And therefore, I can write this as determinant of P inverse times the determinant of lambda I minus A times determinant of P. Now, what can I say about these things? Well, determinant of P inverse, another property of determinants is that that's 1 over determinant of P. And determinant of lambda I minus A, well, that's characteristic of A. And this is the same, and then the determinants cancel, determinants of P cancel, and you get the characteristic polynomial of A, which is what I wanted to prove. You can cancel these because these are just characteristic polynomial of A is just a polynomial, and determinants are just not scalars. They're not matrices. So I can move them around and cancel those out. So similar matrices give me the same characteristic polynomial. And because of that, I can now define the characteristic polynomial of a linear operator. So you have a finite dimensional vector space. You have a linear operator from V to V. And then you pick whatever basis you like, because what we just proved, the basis doesn't matter. You just pick a basis, and the characteristic polynomial of T is defined to be the characteristic polynomial of the matrix of T with respect to that basis. We had already defined what the characteristic polynomial of a matrix is. Now we're saying that if you want the characteristic polynomial of a linear operator, you just find the characteristic polynomial of any of the matrices associated with it with respect to any basis. And we denote that polynomial by Char T. Okay, so now for a final example, let T be a linear transformation from R3 to R3 defined by T of XYZ. XYZ is a typical element of R3. So where does it go? Where does this function send it? It sends it to minus 2x plus 9y minus 12z, 6x plus y, 9x minus 9y plus 13z. What is the characteristic polynomial of this linear transformation, this linear operator? So our plan is to find a matrix for this linear transformation and then find its characteristic polynomial. So you might start with the standard basis for R3. To find a matrix for a linear transformation, you need a basis. The standard basis 1, 0, 0, 0, 1, 0, 0, 0, 1. How do you find the matrix of the linear transformation with respect to that basis? Look at the videos that tell you how to find matrices of linear transformations, but you can take that first basis element 1, 0, 0, you plug it into the function. That amounts to putting x equals to 1, y, and z equals 0, and you will get minus 2, 6, 9. And then you write that in terms of the standard basis, except since this is the standard basis, it's already written in terms of the standard basis. And so that will be the first column of the matrix. Likewise, 9, 1, minus 9 will be the second column, and minus 12, 0, 3 will be the third column. Therefore, the matrix of T with respect to S will be this matrix. And so what you could do is now find the characteristic polynomial of this matrix. You find lambda I minus this matrix. You get a 3 by 3 matrix, find the determinant of that, and go from there. And then that determinant will be the characteristic polynomial. However, remember that we don't have to use the standard basis. You might want to use this other basis. This is sort of a weird basis and came from nowhere. But you might want to use the basis 1, 2, 1, minus 1, 1, minus 1, minus 1, 0, 0, 4, 3, which is another basis for R3. These are 3 vectors in R3 that are linearly independent, and they form a basis for R3. So how do you find the matrix of T with respect to those? Well, you plug in 1, 2, 1 into the function, see what you get. If you do that, you will get 4, 8, 4, which is just, and then you have to take that 4, 8, 4 and write it in terms of B, find its coordinates with respect to B. And for that, you need 4 of these, none of these, and none of those. And so the first column of your matrix will be 4, 0, 0. In fact, the matrix that you will get will be the matrix of T with respect to B will be this nice diagonal matrix for 0, 0 as the first column, 0, 7, 0 as the second column, 0, 0, 1 as the third column. And then because the characteristic polynomials of linear transformations are independent of which basis you use, you can find the characteristic polynomial with respect to this basis. And then that's very easy because the characteristic of T is going to be the characteristic polynomial of this matrix, the matrix of T with respect to B. And for that, you have to find the determinant of lambda I3 minus that. So what do you get? You get lambda minus 4, lambda minus 7, lambda minus 1 down the diagonals and 0 everywhere else. The determinant of that is just the product of those. And so the characteristic polynomial of that linear transformation is lambda minus 4 times lambda minus 7 times lambda minus 1. That, by the way, is also the characteristic polynomial of this matrix T, and this matrix of T with respect to S. So that linear transformation, this top matrix and this bottom matrix all have the same characteristic polynomial. It's lambda minus 4 times lambda minus 7 times lambda minus 1. And 1, 4, and 7, the roots of this polynomial, are the eigenvalues for all three things, this linear transformation, this linear operator, as well as these two different matrices. Now, you may ask, how did you come up with this weird basis? Where did that come from? And I cheated. What do I mean by I cheated? Well, these are, as we have discussed before, to get a diagonal matrix, you need these to be eigenvectors. And those diagonal elements are the eigenvalues. So I actually first found the eigenvalues and the eigenvectors before I had this basis. And how did I find that? Well, I went back to this original matrix of T with respect to S, found this characteristic polynomial, factored it by noticing actually that lambda equals 1 is a root. How did I notice that? If you plug in 1, you get 0. You can use the rational roots theorem if you remember that from high school or from abstract algebra. And if you plug in 1 equals 0, you get 0. So you know lambda minus 1 is a factor. And then after you factor that, you get a quadratic. And then you can see that 4 and 7 are the other roots. And then after finding the eigenvalues, you can find the eigenvectors. We showed that in a previous video how you do that. And so I actually cheated. If you just started with this linear transformation, you couldn't possibly come up with this basis just randomly. You had to go through this other process. In fact, that will be the subject of our next video, diagonalizability, and finding eigenvalues so that the matrix of a linear transformation with respect to that basis will be diagonal. This is the end of this lecture, and I will see you at the next lecture.